So we took a look at countdown latch and saw that it had some deficiencies as far as its use in a couple of ways. Like you can't reuse it, you have to recreate a new one. And it's not always the most ideal thing for entry barrier semantics. Now we're going to talk about cyclic barrier and see how that can be used to overcome some of the limitations with countdown latch. So cyclic barrier, as we'll see here in a second, can be used to allow a set of threads, or parties as they're called, to wait for each other to reach a common barrier point before proceeding. And this is a little bit more interesting, although it works in very, very stylized ways. So cyclic barrier implements yet another Java synchronizer, barrier synchronizer. It's well suited for fixed size, cyclic entry and/or exit barriers. So it's used for a fixed size number of threads, where you know the number of threads or parties in advance that are going to wait for all the other threads that are part of the group to finish before the group can begin again or proceed. The other thing you can do with the cyclic barrier is you can allow the count to be reset at any given point. So unlike countdown latch, where you got it for one shot and that was it, with cyclic barrier you can reset things. Now you have to be prepared to be resetting things because there's an exception that gets thrown, but you'll see how it works here in a second. This particular implementation is its own thing. It does not apply the bridge pattern. It doesn't leverage the abstract queued synchronizer framework. It's got its own implementation, which is quite interesting to look at. And under the hood, it uses mechanisms that you're familiar with from other things we've talked about in Java synchronization. So let's talk about the key methods in the cyclic barrier. So the constructor initializes the cyclic barrier instance so it will trip. Don't think of trip as like stumble. Think of trip like tripping a circuit to turn it on or off, right? You trip a circuit breaker, for example. It will trip when a given number of parties wait on it, when all the parties have finished waiting on it. So here's the constructor. You can give it the parties count, where parties equal the number of threads. I don't know why they called them parties. It's kind of goofy, but that's what they called them. And keep in mind that you have to have a fixed number of these things. And we have parties, and we can also see that there's a second constructor that takes another parameter, and this parameter is called a barrier action. And this is an optional parameter, which you can either ignore. I mean, you can either call the constructor that doesn't have one, or you could even give a null to the second constructor. Kind of silly thing to do, but you could. And if you have it null, it just gets ignored. If it's non-null, if there's a barrier action that's defined, this barrier action's run hook method is called back when the barrier is tripped, but before all the threads start to execute again. So it's kind of a hook that you can use to do something. And the key thing to remember is that this barrier action is performed by the last thread that enters the barrier, right? So when, if you have four parties or threads that are in your cyclic barrier, the first one gets there, fine, it waits. The second one gets there, fine, it waits. The third one gets there, fine, it waits. The fourth one shows up. Then, if there's a barrier action, it gets triggered with the lock held, and the other parties suspended, or threads suspended. And then, after that barrier action returns, then they all get a chance to advance to the next phase. So you typically use this to update any shared state before the parties continue. So let's say, for sake of argument, that you're doing some kind of gang scheduling to process parts of an image. You bring a big image in, you're going to have the different threads working on different parts of the image, looking for stuff or whatever. And after they're all done with that image, then the barrier action could say, bring a new image in, and then start the whole process over again, working on that image to process it, whatever different parts of the image are being worked on. So the count is basically reset to the initial number of parties after the barrier's tripped. So when the nth one shows up, barrier action gets called back. Whatever happens, happens. If there's no barrier action, then nothing happens. The count gets reset, and the threads can start over again and do the cyclic barrier processing once again. So there's really only one method for the most part that matters, and then there's another one that you can use if you want to reset things explicitly. So the main method that gets invoked is await. And what you do here is, if you're a thread or a party that's a party to this CyclicBarrier protocol, all the threads start up and they all call await. And they all block in await until everybody in the set of threads calls await, at which point the barrier action, if there is one, gets triggered, and then they all start over again. Now, obviously, other things can happen when you're awaiting. You can have the barrier reset. We'll see what that means in a second. You could have the thread be interrupted. So you don't just wait indefinitely. Other things can get you out of awaiting. But most normally, you wait for things to all reach a certain stopping point or a common stopping point. You can also, of course, and await returns the arrival index of the thread at the barrier. Most of the time, that information is meaningless to you, but you can also use it if you want to know when the last thread gets there. So if you don't have a barrier action, then you can basically do this. If barrier.await equals 0, then you're the last one to arrive. You can also have a timed await, which just says don't wait indefinitely, wait up to this period of time. And then the last method here is reset, and that just resets the barrier to the initial state. So if it was 4 or n or whatever, it'll reset it to that. And if anybody was waiting on the barrier, they will be awakened and they will return with a broken barrier exception. So you have to be prepared for a broken barrier exception if you're a waiter in a cyclic barrier. That just says that you decided to not have everybody wait for that thing. It's kind of an uncommon thing to do that, but it's there to avoid everybody just waiting forever. Now that you've got an overview of what a cyclic barrier is and some of the key methods it provides, let's take a look at how to use one. This particular example will be very much like what we looked at before, except now we're going to use cyclic barriers instead of countdown latches. And you'll see how this will close one of the limitations with our earlier example. So this again is the GCD test. It's the road race test where we're going to go out and test drive these different implementations and see which one performs the best, except this one is the cyclic barrier implementation. Here's what the code looks like. You can see it's roughly about the same in terms of what it does, but it uses a few new features and it's a little bit more robust for reasons we'll see in a second. So here's what we're going to do. We are going to make a bunch of tests, one test for each different way of doing GCD. And then we're going to create two cyclic barriers. One is an entry barrier and one is an exit barrier. You can see what we do here is we make a cyclic barrier, which is the number of tests, let's say there are 4, the number of tests plus 1. What's the 1 for? Right, so the main thread, right? We had an extra one because we want to include the main thread in that. Remember that when you do the next assignment, because you'll need to remember that. You can also see here, so we make the entry barrier is number of tests plus 1. The exit barrier is the same thing, number of tests plus 1, because we're going to basically include ourselves in this computation too. We also provide a barrier action. And this barrier action is going to be called, as we talked about before, between the point when the last thread shows up to the barrier and when all those threads can start to do their thing again. And so in this particular case, we're just going to reinitialize the data structure that's used internally in order to make the testing run more efficiently. So we're just giving something to reinitialize or do something here in the barrier action. All right, so what we're going to do here, let's say that we're going to run this test for S cycle times, where that's 3, for example. We're going to run our little competition 3 times for, say, 4 tests. So that's the number of cycles. And we might do this, maybe we're going to time things. We want to make sure that we give them all a chance to run multiple times to get rid of any perturbations that might affect the performance. What we're going to do here is we're going to make a new thread with the entry and exit barriers. We'll see what that does in a second. And then we start that thread for every one of the tests. So notice what we're doing here. This is kind of funky. This is actually a nested loop, but we're doing it with the for each method on GCD tests. So GCD tests is a list of GCD tuples where there's one tuple per test. And then we're going to iterate for I equal 1, I less than, or cycles equals 1, cycles less than or equal to S cycles. So that's the number of iterations we're doing for the cycles. And then for each cycle, we have a for each method that runs each of the tests with a new thread that gets started. So just kind of illustrating how this all works. That'll start things off. So for any given point in time, we're going to have all the threads running, say start test, but we don't actually start running yet. The entry barrier await gets called. Entry barrier await will block until all the other threads await on the cyclic barrier. So this is actually a more robust way of starting because nobody starts until they're all ready to start. So that's better than the countdown latch version. And that's why we included a +1 when we made the cyclic barrier, because we have GCD test.size number of worker threads. So let's say there are 4 of them, plus 1 more for the main thread that's waiting for all the other guys to get ready to run. So we call await here. That will make sure we block till everybody else is ready to go. Then we go ahead and run the tests. And then exit barrier await is called. And that's the same idea. The main thread is included in the number of waiter parties because we want it to wait for everybody else to finish too. Okay, so that's basically how we make the main thread wait for everything else. Here's the GCD cyclic barrier tester, which is a runnable, so it can run in a thread like we showed over here, where we create and start that thread. The constructor stashes away the entry and exit barriers as cyclic barriers like we did before. And then here's the actual run method. So you can see, remember, this run method will be called for every thread that's part of the tests we're running, one thread for every different GCD test combo we've got. We call, every thread calls entry barrier dot await. Remember, that will block until everybody calls the await method, at which point the test can be run, and they'll all start at the same time or close to the same time. As close to the same time as can be the case with a multi-core processor that's scheduled. And after the test is done, then we call exit barrier await. And that again will block until everybody else calls await as well. So that's basically how we can coordinate this. So this approach is better than the one we saw before because it'll really force the threads to stop or pause or park until everybody else is up and running. So it's a cleaner solution than the approach that we saw before with countdown latch.